Conventional wastewater treatment, aerobic treatment, is based on aerobic processes that were developed in the 1900s. They basically take the organic material in domestic wastewater and burn it using aerobic microbes. The challenge with that approach is that it consumes a lot of energy to aerate the water, and it also produces a large amount of biosolids that have to be disposed of. So these two key challenges really afflict the industry and impede the ability of the wastewater treatment sector to move on to a more sustainable paradigm. Another big issue with the conventional aerobic paradigm is that they produce nitrous oxide emissions. And nitrous oxide, I think, is about 300 times worse as a global warming compound compared to carbon dioxide. So even a very small amount of nitrous oxide emissions from conventional aerobic treatment plants do a lot to harm the climate and are a major component of the climate impact of wastewater treatment plants. So what can we do? What do we think about? Well, we think about domestic wastewater as a set of resources. There's water, there's organic matter, there's nutrients, there's other resources that I won't talk about today. But how can we use those resources to provide benefits for society? Well, we can generate clean water, we can provide nutrients in the form of fertilizers for food, and we can also provide renewable energy. And if we can achieve all three of those things, then we're using domestic wastewater as a cornerstone to enable energy efficient, sustainable cycles. Now, looking at anaerobic wastewater treatment specifically in that context, where would that fit? If you look at a very simplified diagram of conventional wastewater treatment, you start here on the left with primary treatment. Wastewater flows in, you go through these settling tanks. Any material that will sink to the bottom of the tank can get sent to anaerobic digester for energy production, but the rest of the water flows on to aerobic secondary treatment, where we blow air into the water to allow aerobic bacteria to consume the remaining organics. We settle out those bacteria in the secondary clarifier, send those also to the anaerobic digester, but we don't get to recover a lot of the energy in that set of secondary solids coming from the secondary clarifier. Then the water goes on to post-treatment. What I'm talking about, or what we're aiming to do, is an anaerobic MBR process, anaerobic membrane bioreactor process. So a simplified schematic, you have your primary treatment, you still send as much of the solids as you can to anaerobic digestion, because anaerobic digestion enables you to produce energy. But we replace the aerobic process with an anaerobic secondary process. We eliminate the aeration. And what that enables us to achieve is we reduce the energy consumption, we increase the renewable energy production while reducing the amount of solids that are produced and reducing the greenhouse gas emissions. And I have an asterisk there because that's all caveated on making sure we manage that methane properly. What does the system that we use look like? It's called the Staged Anaerobic Fluidized Bed Membrane Bioreactor, or SAF-MBR is the acronym. It's a two-stage process. The first stage is what you see here on the left. This is called a fluidized bed reactor, anaerobic fluidized bed reactor. It's a vertical tank where we use granular activated carbon inside this reactor, which people are usually familiar with as something that you can see in a Brita filter in your home refrigerator used for water treatment. Here, we're not using it to absorb chemicals the way that it's used in a Brita filter, but rather it's used as a biocarrier. So anaerobic organisms can attach to each one of these little grains of carbon and get retained inside the reactor. And they consume the organic matter that flows past them in the system. We have a recirculation pump that pumps water up vertically through this bed of carbon and keeps it fluidized. So these grains of carbon are falling about as fast as they're getting pushed back up by the water, and they stay suspended in the turbulence of the water column. As they consume organic material in the water, they produce biogas, bubbles of biogas. This is methane primarily, about 85 to 90% methane in this case, and it'll just bubble right out of the water. Most of it will bubble right out of the water, and we can then send it for energy production. The water coming out of the system still has a lot of suspended solids in it. And so what we do to get rid of those suspended solids or retain those in the system is we use membranes, ultrafiltration membranes, which are very common technology now used in a lot of aerobic MBRs. Those membranes hold the solids inside the reactor. We recycle those back into the fluidized bed reactor in order to give them multiple passes on the bacteria. Because the membranes are basically glorified colanders, they will clog up over time with solids. It'll accumulate solids on their surface. So we blow bubbles of recycled biogas across the membranes to agitate them and shake those particles loose. And then we waste a small amount of the biosolids because there is still growth of anaerobic organisms, and we send those off back to the anaerobic digester for the processing. And the effluent from the system can go to polishing for discharge or water reuse, preferably water reuse. This system has been under development now for a little bit over a decade. It started with some lab scale studies in 2009 in South Korea. That grew to some pilot scale studies in the early 2010s, first in South Korea, and then we developed it further here at Stanford at the Codiga Resource Recovery Center. This has been an ongoing initiative that was started by the late Professor Perry McCarty, who worked with a former student of his in South Korea to initially develop the concept and then brought it back to Stanford. After successful demonstration at Stanford, we obtained funding from the California Energy Commission and built a partnership with SVCW and deployed a much larger system, about 5,200 gallons in size, at Silicon Valley Clean Water, which was brought online in 2021. So looking at where that system is located at SVCW, this is an aerial view pulled from Google Maps. This little section right here is the pilot slab where we're doing our testing and demonstration of this technology. That slab is about 40 feet by 80 feet. If you take a look at it as an image, this is our reactor. On the left-hand side is the fluidized bed reactor. On the right-hand side is the membrane tank, and in between is the control panel. Putting some dimensions on that, the fluidized bed reactor is about 6 feet square on the bottom and 20 feet tall. And then the membrane tank has 9 ZWEED membranes. These are one of the industry standard membranes for ultrafiltration, and those fit in a 3x2 by 10 foot tank. Our operating conditions for the engineers out there is we're operating this system at about a 5-hour hydraulic retention time. That's the amount of time that the water stays in the system. A 22-day solids retention time of those solids in the bulk fluid. Remember that most of the biomass is attached to the granular activated carbon and actually stays in the system much longer than that, hundreds of days. And we're operating at a net flux of about 12 liters per square meter per hour on the membranes. And with that, we're processing about 20,000, a little bit over, more than 20,000 gallons per day. Now, looking at the performance of the system, the influent of the reactor is a little bit over 450 milligrams per liter in general. And our effluent, our permeate, is less than 50 milligrams per liter consistently. So that's a 92% COD removal. If you think of a secondary effluent permit is typically requiring BOD concentrations below 30. So BOD is typically about half of COD, and so we're coming in meeting secondary effluent standards with this anaerobic technology. No aerobic polishing, no aerobic treatment necessary to meet those secondary effluent standards. Because it's a membrane system, suspended solids are essentially eliminated in this system. So this is an incredible level of performance for an anaerobic system. As far as I know, it's the only one of its kind in the world that can demonstrate, that can prove and show this kind of performance. Looking at a mass balance, so, a tiny amount of the COD, only about 8% of the COD the incoming COD remains in the effluent. What's going on with the rest? Some of it is wasted to the anaerobic digester. A small amount of it is consumed by sulfate-reducing bacteria, which produces sulfide, and that's a challenge, and I'll talk about it in a second as how we're solving that problem, because sulfide is a problem. And then the remainder, a large chunk is remaining in dissolved methane, which we can harvest. We've got effective tools to extract that methane from the water to be able to put it to beneficial use. And then we've got another fraction of the material of the COD that's being converted into gaseous methane. But there's still something missing in this balance. And in this case, we attribute that to measurement errors and some fabrication defects in the reactor that are probably leading to biogas leakage. And this is the big caveat and the acknowledgement that we have to make here is if we leak biogas, then we're not necessarily improving the climate outcome of this system, because methane is a powerful greenhouse gas. But if we engineer these systems to capture the biogas appropriately, which we know how to do, we can do, and it's done at full scale, then we have all of this methane, all of this COD that's going to methane. 80% of the incoming organics are getting converted to methane, which we can use for beneficial purposes. The most simple, straightforward thing to think about there is you can burn that. Methane is just natural gas. That's the CH4 is natural gas. You can burn it to make electricity. So that we'll get back to the energy balance in a second. The other element of this is to look at how much secondary sludge we're producing. We produce about 0.02 grams of volatile suspended solids. So grams of basically organic material solids that need to be disposed of as biosolids for every gram COD that we remove. That's a 90% reduction compared to a conventional activated sludge process. So we're driving down the biosolids production, the secondary biosolids production, down by 90%. So if you think about that, and then you take the primary solids, which we're still sending to anaerobic digestion, overall, you're reducing your total biosolids production by 30 to 50%. So that's a huge reduction in the number of trucks. You can think about it, taking 1 out of every 3 or 1 out of every 2 trucks, biosolid trucks, off of the road and not sending them long distances to dispose of this material. So now let's look at the energy balance. So our requirement to run this system is about 1/4 kilowatt hour per cubic meter of wastewater. And our production, if you take the value, the energy value of that methane, take the methane and take regular industry standard assumptions on how you could burn that and produce electricity with it, we end up producing just under 1/2 kilowatt hour per cubic meter of electricity from that methane. So it's a net energy positive process, about 1/4 kilowatt hour per cubic meter of surplus electricity. That is green electricity that you could be exporting to the grid using this process. So now thinking about what the footprint of the system looks like. If we go back to SVCW as currently employing a relatively conventional secondary treatment process, this is an aerial view of the treatment plant. First, you can look at these systems here are the trickling filters that SVCW uses as a pre-treatment for their aerobic activated sludge basins. We wouldn't need these to run the system to treat the wastewater with an anaerobic treatment system. So you could save that footprint. You could fit, and here you can look at the next thing I'm highlighting here are the secondary clarifiers. These are the large settling tanks that are used to settle out the sludge from the anaerobic, from the aerobic activated sludge process. We wouldn't need those either because we use membranes. You could fit the membranes conservatively in about 1/4 of that square footage. Meanwhile, this fourth square here, this is third square that I'm highlighting. These are the dual media filtration systems at SVCW that are used to polish and filter the water coming out of the secondary clarifiers. Because this SAF-MBR uses ultrafiltration membranes, you don't need dual media filtration as a polishing step afterward. So you can save that footprint as well. So you can fit your anaerobic secondary treatment process basically in this remaining area that I've got shown here. But I'm not done, because since you're cutting the biosolids production, the total biosolids production conservatively by at least 1/3, you've got 3 digesters here. Well, you don't need one. You could basically save the space for one of those and operate your facility on 2 of those digesters. And because you're producing a lot less biosolids that need to be dried and managed, all of this infrastructure that you've got on the side here for your sludge drying beds, and the image doesn't show it here, but that sludge storage infrastructure, biosolid storage infrastructure is quite a bit larger at SVCW. You don't need that either. So all of this footprint, what could you do with it? Well, you fit your SAF-MBR treatment process to meet secondary effluent standards within this pink square here, and this remaining square footage that you've saved this is now the space that you can use to pursue water reuse. One of the big challenges of a lot of wastewater treatment plants is they're constrained in footprint. And if you want to start adding additional treatment processes to achieve water qualities for water reuse, the question is, where do you put them? Well, there you go. So we've come up with this, we're really excited about this approach because you can basically intensify the process. You can treat more water in a smaller footprint and free up some footprint that you can use for water reuse. So what does water reuse look like using a SAF-MBR? Well, with funding from Prop 1 and from the U.S. Bureau of Reclamation, that's what we've been exploring. We're looking at a treatment train that takes the effluent from the SAF-MBR and polishes it. One of the steps, so here's the SAF-MBR that it's used for treatment of organics and for energy recovery. We take the effluent from that system and we put it through another relatively new and modern process called a membrane aerated biofilm reactor. And we use that system to remove the sulfide that I mentioned is produced in the system. How does an MABR work, a membrane aerated biofilm reactor? We've got the system that we've been demonstrating or testing at SVCW. We have water from the SAF-MBR coming in with some hydrogen sulfide, S2- as it's listed. We've got the Z-lung MABR membranes inside this tank. What those are is they're air permeable membranes. We pump air into the membranes and that air flows from the inside out into the water. And it flows, as you look at a cross section of that membrane, you've got air coming in the center in what's called the lumen. And it's flowing out, diffusing out through the wall of the membrane into a biofilm of organisms that is living on the surface of those membranes. So you're not wasting a bunch of energy trying to pump air into the water. You're just pumping the air specifically into the bacteria that need it. And you're not having to send any extra air into the ambient water. So this surface of these membranes gets cultivated and colonized by sulfide oxidizing bacteria. And we achieve a very high degree of sulfide removal, greater than 99.9%. And so we end up with effluent sulfide concentrations that are less than 5 micrograms per liter. And this is water that would then be should be well suited for certainly for discharge and probably for downstream water reuse. So what we've been testing, because this MABR adds back some microbes into the bulk fluid into the water, we add an ultrafiltration step on the back end to keep the water solids free, remove all the particulates. And then we would want to add ultraviolet disinfection to that in order to meet Title 22 water reuse requirements. This is a treatment train that we're in the process of testing at SVCW to demonstrate viability of achieving non-potable water reuse, Title 22 non-potable water reuse standards using an anaerobic treatment train. Now we think about, okay, well, I've just added a bunch of treatment processes. What does that do to my energy balance? Well, the SAF-MBR produces a surplus of a quarter kilowatt hour per cubic meter of wastewater treated. The MABR can be operated very, very energy efficiently to remove the sulfide, less than 1/100th of a kilowatt hour per cubic meter. The ultrafiltration membranes would take about another 5/100ths of a kilowatt hour per cubic meter. And the ultraviolet disinfection would use about 8/100ths of a kilowatt hour per cubic meter. Add that all together, and we're still producing a surplus of about 1/10 of a kilowatt hour per cubic meter of renewable electricity. If you add the surplus of renewable electricity that you can produce when you're anaerobically digesting the primary solids in the system, you end up with an overall energy balance where you're still exporting about 0.2 kilowatt hours per cubic meter of renewable energy, renewable electricity to the grid. So we think this is an unprecedented outcome and really exciting because you could be producing water for non-potable reuse, purified water for non-potable reuse, while also exporting renewable energy to the grid. But we're not stopping there. So what you could also think about and what we are going to be testing in the next couple of months, we'll start these tests at SVCW, is instead of going for non-potable reuse, let's go for potable reuse. Let's put reverse osmosis and advanced oxidation processes. These are the conventional components of a full advanced treatment train for potable reuse, and try and achieve the water standards for potable water reuse and see what the energy balance is. That's what we're going to be working on in the coming months. So stay tuned for more results. In the meantime, the big punchlines of our work, here's some pictures of the water coming. On the left, you see the water coming into our system. In the middle is the water as it's circulating inside of the reactors. The water gets concentrated a little bit because of the membranes. But then on the right, you see the water coming out of the system through those membranes. So very pristine, crystal clear looking water. So our system, the SAF-MBR, enables very high quality effluent, matching the standards of conventional aerobic processes. It's the first energy positive secondary treatment system that we know of. We achieve a 90% reduction in the production of these secondary biosolids, which are a major concern or challenge of management for wastewater treatment plants today. We do all of this in a smaller footprint, which frees space up for water reuse. So we think that by demonstrating this, we're traveling toward a future where water reuse and green energy export can become the staples of wastewater treatment plants. With that, I want to thank, we've done this work with a tremendous slew of partners, certainly our funding support from the California Energy Commission, U.S. Bureau of Reclamation, and the water boards through Proposition 1, and a number of other partners that have helped us implement this. But most importantly, which is why they're at the very top of this page, SVCW has been a true champion of this work. And I can't emphasize enough how critical that is, because new technologies that can transform our sector won't make it unless there are utility partners that are willing to step up and help demonstrate these technologies at a credible scale. And that's a big challenge for utility to do, because they've got to meet permit, they've got to operate very complex multi-million-dollar facilities 24/7 under a lot of strain and a lot of pressures from all sides. And SVCW has been such a fantastic partner in showing the vision and leadership to take this task on. And I can't thank them enough. I think they deserve a tremendous amount of credit for this leadership, and I really admire the work that they do every day. With that, thank you so much, and happy to take some questions.
Great, thank you, Sebastien. This was I'm still processing a lot of just things that you've mentioned, even in terms of the just the treatment train as it exists now, and then looking ahead. Do you have, by the way, in terms of the Title 22 standard, there's the Title 22 standard, and then you're talking about doing potable water reuse, adding other, I guess, cars to the train. But where do you stand today, just regarding the Title 22 standards?
So there's a couple different things that need to happen for Title 22. So to get an actual Title 22 system up and running, you need an engineering. There's this sort of chicken and egg challenge, where someone who wants a utility or a permitted entity that wants to start recycling water and produce Title 22 water needs to initiate a project and then work with an engineer who will provide an engineering report, essentially certifying that the proposed treatment process will achieve the Title 22 water quality requirements. And so the challenge with that is, of course, an engineer is not going to make that statement without having data to back it up. And a utility is not going to build a system to generate the data without having the engineering report. So what we're doing here is solving that problem, essentially in a de-risked environment, because the effluent from this facility currently goes back to the headworks of SVCW. And so we can generate the data necessary to show that we meet the requirements for Title 22, and that this system can meet the requirements for Title 22, which will then give consulting engineers and utilities the confidence that they could proceed and build such a system like this, scale it up and build it for implementation. So, we're meeting the requirements in terms of having a fully oxidized water by removing the BOD and by removing any sulfides, so that you're removing the oxygen demand of the water. And then the other requirements are disinfiltration and disinfection, which are met essentially through the ultrafiltration process and through UV. So I'd say, yeah, we're showing the steps to achieve Title 22 non-potable water reuse.
Yeah, so there's some questions I just wanted to run through. One from Brian Schmidt, who won a prize earlier in the previous round. Sounds like the sulfide removal results in sulfate, and what is done with that?
The sulfur species actually it's a mix. There's sulfate production, there's some elemental sulfur production as well. And there is also some thiosulfate that's produced, and that's left in the water. So that can present a challenge for, say, for further treatment with, it needs to be managed and considered when looking at reverse osmosis, for example. But you have to bear in mind that when the water came into the plant, it was sulfate to begin with, right? So if you look at a conventional aerobic treatment process, it's not going to remove the sulfur species either. It's just going to have sulfate coming in and sulfate coming out. So this process, it's not entirely returning that sulfur to the sulfate as it was, because some of it's going out in different species, or some of it's being removed as elemental sulfur. But it's mostly that. There's another question from Peter Dreckmeyer about how might these technologies contribute to denitrification of wastewater into the bay and reduce toxic algal blooms. There's a variety of different ways you could do this. So one of the things that we're starting to look at and test, we've been operating this MABR specifically with the intent of minimizing and eliminating and preventing conversion of the ammonia in the wastewater into nitrate. So this is an anaerobic system. So all the nitrogen that comes in the form of proteins or ammonia will come back out of the system in the form of ammonia, which can be, currently, as Peter's well aware, currently most of the wastewater treatment plants around the bay do not have ammonia or nitrogen limits. Some of them do. Palo Alto has an ammonia limit, but not a nitrogen limit yet. That's in the process of changing. And so then the question is, what do you do? Well, one approach is to look at biological nitrogen removal technologies. What we've actually been looking at is optimizing if you're trying to do potable reuse, which I submit is the highest and best use of water. And so that's where my mind goes. In a potable reuse scheme using RO, there's actually mechanisms where you can optimize that RO to concentrate the ammonia, basically use the reverse osmosis process to remove the ammonia from the water. So the water is then ready for going on to advanced oxidation and storage, et cetera, for reuse, for potable reuse. And now you have this concentrate stream, which has a higher concentration of ammonia. And you might say that's a bad thing, but actually the more concentrated something is, the easier it is to recover. And so we're looking at various different technologies where you might be able to recover that ammonia and convert it into a useful fertilizer. And you leverage that for further societal benefits. Basically, the premise is that reactive nitrogen, ammonia, nitrate, et cetera, is a core element. It's critical to keeping billions of people on this planet alive and fed through fertilizer and food. We make that fertilizer with the Haber-Bosch process, which uses very large amounts of energy and high temperature, high pressure to extract nitrogen from the sky and make it into ammonia. And so why philosophically, let's not try and take the ammonia that we have in a wastewater treatment plant and turn it back into nitrogen gas. That's a shame. Let's think about ways that we can try and take that ammonia and economically turn it into a safe fertilizer that we can return to our fields and reduce the amount of energy and greenhouse gas emissions we need to produce ammonia via the Haber-Bosch process. That's the way we're looking at it, but you certainly could do nitrification, denitrification in a future world. You could think about doing partial nitrification in anammox, partial nitrification in CANDU to make nitrous oxide to boost the energy production from your combined heat power plant. There's a few different ways you could go about it.
Mm-hmm. Yeah, that in itself is an interesting topic to deal with. So, Peter, thanks for the question. And Sebastien, thanks for the answer, which kind of, if not raises more questions, it certainly opens up a lot of thoughts in that, just in that area of denitrification. As you said, getting philosophical about it. But well, it's interesting to be philosophical, but then also apply some good engineering to different things that you've been working on. So, well, thanks for finally coming to visit us at Waterpalooza. I think a couple years ago, this was, I think this was still an early pilot, an idea. And I think you just kept saying, I can't break this thing. We build bigger and bigger, versions of this, and it resists my attempts at breaking it. So I hope that's still true, and best of luck for just even these other stages, and getting through doing the Title 22 dance, as you've mentioned, as well.
Thank you. We're more than happy to talk to, so start sharing these data that we have with the engineering consulting community, both so they can kick the tires and start maybe exposing finding any blind spots that we've missed so far, and help strengthen, because that will ultimately help us strengthen the case here. And the goal is to develop the confidence in the industry that's necessary to be able to build these systems at scale, at a full scale, and start implementing and delivering on their promise. So
yeah, well, this is a great kind of demonstration, and I mean, you always think of like whatever, faster, cheaper, smaller, better looking, I mean, but this demonstration has an abundance of attributes, as you mentioned, and then even just the energy situation is considerable as well. So it was worth the wait.
Thank you, and hopefully soon enough we'll be able to come back and share some exciting results from the testing of the systems for potable reuse trains, and see what that looks like.
We have wet talks. Take care.
Stay tuned. Take care.
Yes.